People hear maximum risk and imagine one guaranteed disaster. But the real question is not whether the Manila Trench is dangerous. It is why the same offshore source could place much heavier danger on some coastlines than others. By the end of this episode, you'll understand why Manila Trench risk is uneven, what makes that danger rise, and what helps bring it down. And from the start, one boundary must stay clear. This is a scientific scenario, not a prediction. No schedule, no countdown. No soon. Because maximum risk is not one number. It is a stack of conditions. Far offshore, west of Luzon in the Philippines, the Manila Trench is a subduction boundary. It sits out of daily view, but not out of the hazard picture. And if a large rupture were to occur there, the source would matter, but the source alone would not decide everything. That is the main lens for this episode. Maximum risk is not just about the trench itself. It is about how source, exposure, vulnerability, and constraints stack together. So begin with the first layer, the trigger. In a maximum risk discussion, we start with a large offshore earthquake scenario along the Manila Trench. That means strong shaking potential for some areas, and, if tsunami-generating conditions align, added coastal concern for the most exposed shorelines. But even here, one scientific rule matters. Tsunami is not automatic. It depends on how the event behaves, how the seafloor moves, where the rupture concentrates, and how energy is directed toward real coastlines. That is the first takeaway. The source matters, but it is only the first layer of risk. Now we move from the offshore source to the places that receive it. If a large Manila Trench scenario were being evaluated, the first coastlines we would study are those that face the open sea toward the offshore source. Why? Because orientation, distance, and coastal shape influence exposure. As broad examples for orientation, not guarantees, this can include west-facing Luzon corridors from the Ilocos coast down through La Union, Pangasinan, Zambales, and Bataan. It can also include parts of Occidental Mindoro that face west, depending on the earthquake's location offshore and the direction of energy. And this is where a common misconception breaks apart. A country is not one coastline. An island is not one exposure zone. The same offshore event does not push risk equally into every shoreline. A more open, directly facing stretch of coast does not carry the same profile as a more sheltered or differently oriented one. A low-lying shoreline does not carry the same profile as a more elevated coast. A port district, river mouth, or bay edge community does not carry the same profile as a farther inland area. So here is the second takeaway. The same offshore event does not create the same danger everywhere. Now add the next layer, vulnerability. Risk rises when exposure meets weak ground, weak structures, and weak systems. In the short term for people, danger may begin with strong shaking itself, especially where buildings are vulnerable, slopes are steep, or falling hazards are likely. And if tsunami conditions align in the more hazardous direction, concern can extend to low-lying coastal districts, ports, river mouths, and shoreline corridors where fast-moving water, strong currents, and flooding potential matter. Notice what this means. Maximum risk is not just big earthquake. It becomes more serious when a large offshore event meets exposed coasts, low elevation, limited access to higher ground, vulnerable structures, concentrated coastal activity, infrastructure that is hard to replace quickly. Ask yourself now, are you right on the coast or farther inland? And if you are coastal, how quickly can you reach higher ground? In minutes, not kilometers. That is not fear framing. That is practical risk framing. Now we move to the third layer, constraints. This is the part many people underestimate. even when people understand the hazard, response can still be slowed by real-world limits. Narrow roads, bottlenecks, nighttime conditions, dense shoreline populations, limited transport, communication gaps, confusion after strong shaking. For places, the constraints can include coastal roads, port facilities, shoreline infrastructure, bridges, power systems, water systems, districts with limited redundancy. This is where Manila Trench maximum risk becomes more than a source question. It becomes a system question. What makes danger worse? Danger increases when exposed coastlines face the offshore source directly. Local terrain or urban layout slows movement. Roads or evacuation options are limited. Low-lying areas concentrate people and infrastructure. Buildings and lifelines are vulnerable. Warning, understanding, or response is delayed. What helps reduce danger? Danger is reduced when communities understand their exposure. Access to higher ground is clear. Routes are known in advance. Buildings and critical systems are more resilient. Ports, roads, and utilities have stronger backup capacity. Preparedness turns minutes into action instead of confusion. That is the third takeaway. Risk grows when exposure, vulnerability, and constraints stack together, and it drops when resilience and access improve. Now step back and look at the full pattern. Why can one Manila Trench scenario produce uneven danger across the Western Philippines? Because maximum risk is not a single dramatic number. It is the alignment of multiple conditions, where the source is offshore, how the event behaves, which coastlines face it, how local geography receives it, how vulnerable people, buildings, and lifelines are, how quickly movement and response are possible. That is the real aha point. A trench does not create one identical outcome for every nearby coast. The same offshore source can produce very different consequences depending on where energy is directed and how real places are built, shaped, and connected. So what does this mean in practical terms? If you are inland, your risk picture is different from a directly exposed low-lying shore. If your coast is elevated and movement options are clear, your situation is different from a route-constrained shoreline district. If a bay, port, or river mouth concentrates exposure, that matters too, even when it is not the first place people imagine. This is why maximum risk must be understood as uneven, not because science is vague, but because geography is real. And one more boundary must remain firm. For any real event, follow official bulletins and local authorities. In the Philippines, that includes FIVOLC's advisories. Science can model scenarios. Science can explain mechanisms. Science can show why some places may face more concern than others. But science cannot provide an exact schedule for future earthquakes. And it cannot guarantee exact local outcomes in advance, because the most important details are measured from the real event itself. So this episode is a scenario, not a prediction. The exact timing of a Manila Trench rupture cannot be predicted. But maximum risk is not random. It is shaped by exposure, vulnerability, and how real coastlines respond. And that is the final truth. Maximum risk is not one number. It is a stack of conditions. Understanding that stack does not create fear. It creates readiness. And readiness, built on science, clear routes, resilient systems, and calm awareness, is what helps protect communities when nature moves beyond our control. If you like this video, please consider subscribing for more calm, science-based documentaries about our planet, and feel free to share it with someone who might find it meaningful.